All right, continuing on with probability. We're going to skip this guy for now. Mr. and Mrs. Smith have 2 children. What is the probability they have a boy and then a girl? So first, you have to think about what are all the possibilities with having 2 children. All right, so let's just list those real quick. Let me get a pen up here. So they could have a boy and a boy. They could have a boy and then a girl, or they could have a girl and then a boy, or then they could have a girl and a girl, right? So 4 possibilities, and that's it. So what's the probability they had a boy and then a girl? So which of these options does that include? Remember, probability is the division, the ratio of successful outcomes to all outcomes. There are 4 total outcomes. How many of them satisfy this situation? Boy and then a girl. Well, it would have to be this one, right? That's the only one, right? So it's going to be 1/4. So that makes sense. This works because compound events are independent. So a compound event is when 2 different things happen. So having a boy is one event, having a girl is a second event. Having a boy and then a girl is a compound event. Okay, these are independent. The odds of having a girl the second time have nothing to do with having a boy the first time. The first event does not influence the second. Okay, so a compound event is made up of 2 or more simple events. Joint probability is the probability of compound events happening. So the probability of having a boy and then a girl together. What's the probability that specific scenario occurs? Independent events are 2 events where the outcome of one has no effect on the other. It's like rolling a 2 and then rolling a 6. Rolling a 6 does not get more or less likely based on whether or not you rolled the 2 to begin with. They're just 2 things happening that have no effect on each other. Dependent events happen when the outcome of the first does have an effect on the second. So that's like drawing cards from a deck without replacing them. Depending on what comes out the first time, the probability for the second card may change. Go ahead and pause this if you need more time on this screen. I'm going to keep moving. So if 2 events are independent, right, and that's the key right here, is these are for independent events. All you need to do is multiply the probability of each thing happening together. So it's the product of the 2 probabilities. Okay, so probability of rolling a 2 and then a 4, well, there's 1 2 out of the 6 options, times there's 1 4 out of the 6 options. Probability of rolling a 2 and then a 4 is 1/36. So it's not crazy likely. Okay. Probability of dependent events is very similar, but with one key difference. It's still just the 2 probabilities, but the second probability is the probability of B happening, assuming that A already happened. Okay, so what's the probability of B happening, assuming A has already happened? So these 2 formulas are probably what you want in the notes. I'll give you a second to write these down. They'll make more sense once we start using them here. So just copy these 2 down, make any other notes you need, go ahead and pause if necessary. I'm going to keep moving here. Okay, first we're going to state whether each of these scenarios is independent or dependent, and then we're going to calculate its probability. So statement number 1, you roll 2 dice. Find the probability you roll a 6 and an odd number, so 1 on each die. The question is, does rolling the first die, or does the outcome of the first die, affect the second one at all? If I get a 6 the first time on die number 1, does that have any effect on the second die being an odd number? It does not. So these are independent events. Okay. So what's the probability you roll a 6? Well, that would be 1 out of 6 times. What's the probability you get an odd number? Well, there's still 6 options. How many of them are odd? 1 is odd, 3 is odd, and 5 is odd. So that would be 3 out of 6. Multiply those, I'm going to get 3/36. We always reduce probability. That's 1/12. So 1 out of 12 times, I will roll a 6 and an odd number. The other 11 times, I'll get something else. Statement number 2. You draw 3 cards from a deck without replacing them. Find the probability of getting the 3 cards in the following order: diamond, then a club, and then not a club. So first we have to determine dependence. Are these events independent or not? Do the odds of drawing a diamond depend, or sorry, of drawing a club the second time depend on the odds of drawing a diamond the first time? So let's start by thinking of it this way. What are the chances of drawing a diamond? There are 13 diamonds out of the 52 cards. Now, we are not replacing them, right? So I'm holding 1 card and I draw again. Well, now there's only 51 cards in the deck. And whether or not there are 13 clubs left depends on what the first card was. So these are dependent events. right? There are still 13 clubs because we are assuming that I got a diamond the first time, and that's where this comes into play, the probability of B following A, because the probability of drawing a club could have changed if we accidentally drew a club the first time. So to do this second probability, we have to assume that what we wanted to happen happened. So the chances of drawing a diamond were 13 out of 52. So we got a diamond, let's say. So now the odds of drawing a club are still 13, because there's still 13 clubs, but there's only 51 cards. Right? And then not a club. So we've drawn a club and we've drawn another card. There's only 50 left in the deck at this point. How many cards are not clubs? Well, normally there would be 52 minus 13, right? There'd be 39 cards that are not clubs. But I drew one of them. I got a diamond. So now there are only 38 cards that are not clubs. So when I multiply all these together, we're going to get some huge number. 13 times 13 times 38. On top, we get 6,422. So out of all the possible outcomes, that's how many of them are favorable. Down below, we're going to have 52 times 51 times 50. It's a much larger number. 132,600. Right, that's fractions not all that helpful. Obviously, it could be reduced, but let's just figure out what the decimal equivalent is. It's going to be about 4.8%, or 0.048. Not very likely at all, right? To get 3 cards in a row the way you want it, it's not very likely. The only thing that makes it even 5% likely is the fact that there are 13 of each and 38 of not a club. So the third draw not being a club is actually fairly likely. Okay, on your own, state whether this is independent or dependent, and then calculate the probability. Okay, so the question is, a search and rescue team believes that there is a 40% chance a plane went down in this area. What is the probability it went down in this area and landed in the forest? So go ahead and pause this and take a second. I want to know, is it dependent or independent, and what its probability is. Go ahead. Okay. First, we need to decide if it's dependent or independent. Well, we can't even talk about what percentage of the area the water takes up unless we know that this is the only area it landed in. So we have to assume it landed here, which means this is a dependent event. Has to be dependent, right? Because there's a 40% chance it even landed there first. Because if it doesn't land in this square, it landed somewhere else in the world, and I have no idea what percentage of the world is forest. So we assume that it definitely landed here. That makes it dependent. Then, so 40% that it even lands in this big square. What are the chances it landed in the forest? Well, the forest appears to be half of the square. So it's 0.4 times half, 0.4 times 0.5. We're going to get 0.2. Or 20%. So, if there's a 40% chance that it landed in this little map, and then half of the map is forest, overall, the chances that the plane landed in the forest is 20%. Hopefully that makes sense. There's one more down here. You flip a coin 3 times. Find the probability of getting tails 3 times in a row. Again, pause for, let's do a minute. Determine dependent or independent, and whether or not, and then what the probabilities are. Go. Okay, so hopefully we all got that this is an independent event. Flipping a coin has no bearing on what the previous coin flip was. So what's the probability of getting a tails? 1/2. What's the probability of getting a tails the second time? Oops, I'm just about to screw this up. 1/2 again. Probability of getting hit tails the third time? 1/2. So 1 times 1 is 1 is 1. 2 times 2 times 2 is 8. So there is a 12.8% chance of you getting tails 3 times in a row, which is actually maybe more likely than you would have thought, considering that it's 50-50. What are the odds of flipping a coin and getting the same thing 3 times in a row? Well, it's 12.8%, which is kind of crazy. It's actually, I would have thought less. Maybe you didn't, but it's actually not as unlikely as you would think. Mutually exclusive events, another vocab buzzword. Mutually exclusive events are events that cannot occur at the same time. It'd be like drawing a 4 and a 5 when you only draw one card. It's got to be one or the other. You can't draw both. So if 2 events cannot happen at the same time, they are mutually exclusive. Like flipping a coin and getting heads and tails. Impossible. Okay? So the probability that either A or B occurs is the sum of their probabilities. We're just going to add the probabilities together because it can't be both. So like if I say what are the chances of flipping a coin and getting heads or tails? Well, they can't both happen. Odds of getting heads is 1/2. Odds of getting tails is 1/2. We add those together, we get a probability of 1. If you flip a coin, you're going to get heads or tails. That's how it works. Okay, so for mutually exclusive events, things that cannot happen together, the probability of A or B happening, but they can't both happen, we just add the probabilities. So when we were talking about joint probability and we wanted things to happen together using the word and, we multiplied, right? Those probabilities got less likely. The more things I try and say are going to happen, the less likely it's going to be. So if we're talking at horse race, right, and you say what are the chances that one horse wins and this next horse gets second and another horse gets third, but you have specific horses in mind, what are the chances you're going to get all three of those right? Not very good, right? But if I say what are the chances this horse gets first, or horse B gets second, or horse C gets third, now it's getting more likely because I'm giving myself more possibilities. So if the word is or, we are adding probabilities. This makes the probability go down, this makes the probability go up. Okay, so let's do one. You are on Park Place. What is the probability that you land on or pass go? Now the question is, are they mutually exclusive? Can I land on and pass go? No, I either land here or I miss it, right? So we are on Park Place. This is us. Hopefully you got that reference. What's the probability of rolling at least a 3? So let's assume we roll 1 die, just for simplicity. There are 6 options. I could get a 1 or a 2. Sorry, excuse me. I get a 3, a 4, or a 5, or a 6. Because at least 3 would work. So that's 4 total options. That's 2/3 or 67%. It's actually pretty likely that I'm going to make it to go or not. Because the only chances that don't work are if I land on a 1 or a 2. Everything else satisfies my situation. Those are mutually exclusive. You're on Community Chest. Right here. Maybe not. Right there. What's the probability you land on free parking or chance? All right, so this would be 1, 2, a 3, a 4, and a 5. So can I land on both? No, those are mutually exclusive. They cannot both happen, right? So I'm going to add those probabilities. I could get a 3, which is a 1/6 chance, or I could get a 5, another 1/6 chance. That's 2/6 or 1/3. So I have a 1 in 3 shot of landing on one of those two things. Back here, we could have also added probabilities, right? I could get a 3, 1 out of 6, I mean, or I could have gotten a 4, or I could have gotten a 5, or I could have gotten a 6. Those all have probabilities of 1/6, which give me the 4/6. We just did it by adding them up beforehand, but if you write it all out, you're doing the same thing that we did just here, right? Adding the probabilities, making things more likely. Now, what if I asked you to find the probability of drawing a card from a deck and the probability of it being a 2 or a diamond? Are they mutually exclusive? Well, we need to know a little bit about decks of cards. There are 4 2s in the deck. 2 of spades, 2 of clubs, 2 of hearts, 2 of diamonds. There are 13 diamonds in the deck, 2 through 10, and then jack, queen, king, ace. But however, there is one card that exists in both. There is a 2 of diamonds. So they are not mutually exclusive. They can both happen. And that's going to put a twist in the probabilities. Okay? Oops, I went too far. If 2 events are not mutually exclusive, if they can both happen, we add their probabilities just like before, but we have to subtract the probability that they both happen. Because in this case, probability of A is getting a 2, and probability of B is getting a diamond, right? So the 2 of diamonds is counted in here. The 2 of diamonds is also counted in here. I am counting a card twice, which isn't fair, because I'm giving it more likelihood. So I also subtract the probability of it both happening, which is going to remove one of those 2s of diamonds. So if I count the 2 of diamonds once here and once here, that's 2 of them. I subtract the 1 of them, and I'm back to just counting the chances once. So that's what makes it fair. Okay, so what's the probability of getting a 2? Well, that would be 4 out of the 52. plus 13 diamonds out of the 52 cards minus the 1, 2 of diamonds out of the 52 cards. So that's going to be 17, 16, 50 seconds, which is 31% approximately. Okay, so let's talk about whether they're mutually exclusive or not, and then do some probabilities. You draw one card from a deck. What's the probability of getting a 7 or a jack? So the question is, can I get both? Can I get a 7 and a jack on the same card? The answer is no, I cannot. So I could get a 7. There are 4 7s in the deck. Or I could get a jack. There are also 4 jacks in the deck. So there are 8 possibilities out of the 52 cards. 8 out of 52, 4 out of 26, 2 out of 13 is 15.4%. Okay. Number 2, drawing a spade or a 9. So the question is, can I get both of those things with one card? And the answer is yes, there is a 9 of spades. So, probability of spades, there are 13 spades in a deck, plus there are 4 9s in a deck. But there is a 9 of spades, so I've counted that card in both piles. I'm also going to subtract the 1 9 of spades, giving me again the 16 out of 52, or the 31%. It's 30.7. I'm rounding up. Hopefully that makes sense. So try this one on your own real quick. Tell me whether it's mutually exclusive or not, and then calculate. Go ahead and pause for 3 minutes and try this. Okay, quality control for a TV manufacturer has determined that 3% of its TVs experience video problems. 1% experience audio problems. 0.2% experience both video and audio problems. What is the probability that a TV will experience either video or audio problems, which will affect the warranty? So the question is, are they mutually exclusive? Well, by definition, no. They could have video and audio problems. If a TV has video and audio problems, I think it's probably just a piece of plastic, but, you know, whatever. So probability of it having video problems, because we're talking about video or audio. So video problems, that's 0.03. Or audio problems, that's 0.01, minus the chances they both happen, 0.2%, so 0.002. So what we really have is 0.03 plus 0.01, that's 0.04, minus 0.002, 0.038, or 3.8%. Right, so this is video problems, this is audio problems, and this is both. Because the question is, or what's the problem that there's any problem at all? Okay. Homework today. There is no homework. All right. Have a great night. Talk to you later.